All right, welcome to lesson 4 for applications of derivatives. Today we're going to be talking about related rates. The two goals here are identifying the constants and variables in an applied context. That's going to also include some rates that we need to be aware of. And two, applying the chain rule when differentiating multiple variables in these related rate problems. So this is going to be like our implicit differentiation that we did earlier in the year. All right, here's our initial scenario. Gina is throwing a surprise party for her best friend and wants to decorate with helium balloons. As she watches the store clerk fill the balloons, she starts to wonder, how fast is the balloon growing? So there's a few different ways that we can talk about the growth of our balloon, right? We can talk about how much air is going in and filling that balloon up, so the volume of the balloon, how that's changing. And we can also talk about the physical size of the balloon in terms of its diameter or radius, right? So we're going to kind of maybe look at both of those ways of thinking about it right now. Okay, question 1. Helium is being pumped into a spherical balloon. What equation relates the radius of the balloon to the quantity of air in the balloon? Okay, so first of all, with a lot of these problems, it's helpful to sort of think about having a picture. So we have a spherical balloon. So here's our sphere, with our center of our sphere. And the sphere has a radius, right? Radius, just like a circle does, denoted by the distance from the center of that sphere to the edge. That's our R. And we'll just say maybe this balloon has a little place right here where the air is going into it, right? Again, helpful to have a picture to accompany our thinking. So what equation relates the radius to the quantity of air in the balloon? So the quantity of the air in the balloon is going to be represented by the volume of this balloon. The volume of a sphere has a simple formula of 4/3 pi r cubed. So the volume is really only based on the radius. Okay? 2, find the radius of the balloon at each volume. Okay, so here are some maybe they collected some data. So at 1 second, the balloon had a volume of 2 feet, and we need to figure out what that radius was. At 2 seconds, the balloon had a volume of 4 feet, and we need to figure out what that radius was. So what I'm going to do here is I'm going to take this formula that we kind of came up with for volume. Well, I didn't really come up with it. This is a well-known volume formula. And I'm going to solve it for radius, right? So what I need to do is I need to divide by these constants here. So the volume divided by these two constants. Volume divided by 4/3 pi. And that would be equal to the radius cubed. So to get rid of that cubing, I need to take the cube root. So here's a nice formula for the radius of our balloon based on the volume of that balloon. And so I'm going to go ahead and do that. I'm going to go ahead and calculate out what the radius was in each of these scenarios. Again, just using this formula here. I'm going to open up Desmos. Okay. So let me clear away what I currently have. And we'll do cube root of the volume. So we start with a volume of 2, and then 4/3 pi. Okay, so here's our first scenario. Just to get in good practice here, it's often good to round to 3 decimal places when working on the AP test. So I'm going to go ahead and round that to 3 decimal places. And I'll go ahead and write that out there on my paper. So let me go ahead and get rid of this Desmos window and go back to the screen. So for the first value here, we had 0.782. And again, that's going to be in feet, just like our volume was in feet to the 3rd power, because we are going to be cube rooting that, right? Our radius unit here is going to be in feet. Now I'm going to go ahead and do these other ones off screen, but all I'm doing is replacing that V value up here with these different volumes to calculate the radius. So for 4 feet, I get 0.985. Again, rounding to 3 decimal places is good practice for our AP exam. 6 feet, we get 1.127. For 8 feet, 8 feet cubed, we get a radius of 1.241. Again, still rounding to 3 decimal places. And then for a volume of 10, we get 1.337. And all I'm doing is changing that V value in my formula to correspond with these different volumes. Okay. Moving forward, we're going to kind of answer some questions based on this. So, number 3, at what rate is the volume changing? So we want to take a look at our volume. Our volume goes from 2 feet cubed to 4 feet cubed to 6 feet cubed to 8 feet cubed to 10 feet cubed. And hopefully you're noticing here that this is a constant rate, right? Because every second from 1 to 2, 2 to 3, it's increasing by 2 feet cubed. Again, our units are consistent, 1 second each, and our volume is increasing by 2 each time. So I'm going to write this out, that the volume is changing at this rate of 2 feet cubed per second. So that is our rate. Now, some notation to go with this. This is known as the change in volume, because that's what 2 feet cubed is. That's how our volume is changing per our change in time. So this is dV dt. That's going to be some important notation for us to be aware of. We're going to a lot of times write our rates in terms of what they mean in this way. So change in volume per change in time. Okay, question 4. Is the radius changing at a constant rate? How do you know? Well, let's go ahead and take a look here. So let's take a look at what's going on between 0.782 and 0.985, and then we'll just sort of compare that here. If it's a constant rate, these rates of change should be the same. So I will go ahead and pull up Desmos to sort of help compare those two rates really quickly here. So we're going to interact with that Desmos screen. So our first rate, so we'll do the second minus first. So 0.985 minus 0.782. So in our first interval between 1 second and 2 seconds, we had a change in our radius of 0.203 feet. 0.203. So right here, it increased by 0.203 feet. And then we'll kind of compare that here. Again, this is increasing. We'll see if it's the same or not. Oh, you can't see what I wrote down. I'll just have to show that here in just a moment. So 1.127 minus 0.985. Okay, 142. So in this case, we again increase by 0.142. So looking at these values, not constant. Easy enough, right? So no, it's not changing at a constant rate. Because during the first interval of time between 1 and 2 seconds, it increased by this amount. And between the interval of 2 and 3 seconds, it increased by this amount. They're not equal, so it's not a constant rate. Again, we could write that out. I'm going to just go ahead and say no for right now. Question 5. The volume of the balloon depends on how much time has passed. Makes sense, right? The volume at 1 second is different than the volume at 3 seconds and 5 seconds and all these others, right? So volume is based on time. Now, it's also true that our radius is changing, and it is also based on time. So we got to be careful there. So we have this formula, V of t, our volume at time t, is equal to 4/3 pi times the radius at time t cubed. So it's really important to note that this radius is not constant each time, right? It's changing. It's changing based on how far along in the blowing up process we are, right? What time are we at? And so it's in this situation, we have an independent variable of time. Now, in related rates problems, time is very, very often going to be our independent variable. Most of our rates are going to be per time. right? So this is pretty common, but something to be aware of. So we have a volume that's changing based on time and a radius that's changing based on time. And we're going to kind of compare and see how these things are related to one another. Okay, so write out an equation for dv dt. So what does that look like? We have our volume formula, which is equal to 4/3 pi r cubed, right? We need to take the derivative of this function with respect to time, d dt. Taking the derivative of everything here with respect to time. So we're going to treat every variable like its own thing, but we're not taking the derivative with respect to v or respect to r, we're taking it with respect to time. So every time we take the derivative of one of these other variables, right, we need to apply the chain rule. We need to add on a times the derivative of volume with respect to time, or times the derivative of radius with respect to time. So anyway, taking the derivative of v, remember, is v to the first power here, so it's sort of like a power rule, but we're just going to get dv dt. Technically, it'd be something like 1 times dv dt, but we don't need to write that one part out. We'll just leave that off. So it's just be dv dt. Okay, that's going to equal. This part here is a constant, so we're not going to mess around with that, but we have r to the third power, right? So it's going to be 4/3 pi times r to the third power. Derivative of r to the third power is going to be 3r squared. Again, because we're not taking the derivative of r, we're taking it with respect to t. We're going to do that as times dr dt, right? Applying the chain rule there because r is dependent on t. R is actually its own function that depends on time. All right, so here we have an equation that relates all of our rates and radiuses and times and different things like that. The change in volume is equal to 4/3 pi times 3 times the radius squared times the change in radius per time. Now, there is some simplifying that we could do here, right? We could cancel out these 3's, so we could get this to look a little bit cleaner, and I will go ahead and do that just to make it look nicer. All right. At the instant, when the radius is equal to 1.5 feet, how fast is the radius changing? How fast is the radius changing? So in this situation, we know that the radius is going to equal 1.5 feet. We know dv dt is actually a constant for this problem, right? Because if we go all the way back up to the beginning, we know that the volume is changing at a constant rate in this scenario, 2 feet per second cubed. So we're going to go ahead and put that in there, 2 feet cubed per second. That is our dv dt. And the thing we're looking for is how fast in the rate is the radius changing. That is dr dt, right? This is the thing that we're looking for. We're looking for how is the radius changing with respect to time. Okay, so what we're going to do is we're going to plug in those values. I'm not going to include units when I do these. I'll think about my units at the end. So we have 2 equals 4 pi times 1.5 squared times dr dt. Sorry, pardon me. So now to solve for dr dt, right? Everything over here is multiplied by dr dt, so I can just divide this entire right-hand side by this, and actually we'll just divide both sides. So it'll be 2 over 4 pi times 1.5 squared, and that's going to equal dr dt. So I'm going to go ahead and use my calculator here, and I'm going to go ahead and just approximate that. This is approximately equal to 0.071 units. Change in radius per change in time, that's going to be feet, because radius is in feet, per time, which is in seconds. So this is how our radius is changing with respect to time. And how fast is that? That is not very fast. It is a positive value, though, so that does indicate that it is increasing. All right, last question here on this front page. Is the radius growing faster when the radius is small or when the radius is large? How do you know? Now, this is one that, if you have experience blowing up a balloon, will make sense, right? Initially, your balloon is flat, and we'll just say the radius is 0, right? At the very beginning, that balloon gets bigger really quick, right? Initially it blows up quite a bit, and then eventually at some point, when it's a little bit bigger, even when you take a really big breath, right, it just gets a little bit bigger, just a little increase, because that difference, even though it's a really small change in radius and the change in sort of how wide that balloon is actually incorporating, a relatively big change in volume, because that increase is all the way around it in 3 dimensions. So at the beginning, the balloon is going to be increasing faster than it will at the end. However, we can be a little bit more technical with this. So let's think about it in terms of our formula up here. So we have dv dt is equal to 4 pi times radius squared times dr dt. Now, we already know that this value is just 2, so we'll just go ahead and replace that with a 2. So if we solve this right here for dr dt, we get this. We get that dr dt equals 2 divided by 4 pi r squared. So let's think about this. The rate of change of our radius, how fast our radius changing, is going to equal this calculation. When r is smaller, this value here is going to be a bigger value. Let's just do a simple calculation. Let's just say r is 1. If r is 1, we get 2 over 4 pi. I know that can simplify, but let's just think about it, 2 over 4 pi. When r is 2, we get 2 over 2 squared times 4, we get 16 pi. Which one of these numbers is bigger, right? This was when r was 1. This was when r was 2. This number is bigger, right? 2 divided by 4 pi is bigger than 2 divided by 16 pi. So you can see here, smaller values of r, because we're dividing by r squared, are going to give us larger rates for how our radius is changing. Again, that's a little bit more technical. Now, we'll go ahead and move on to kind of formalizing some of these ideas. So, related rates problems. We have kind of 5 steps that I'm going to try to go through as we do these problems in the future. We're going to draw a picture. I didn't really draw a picture of it in that previous problem. I mean, I kind of did, but, we'd want to draw a picture, label it. We have our balloon, air going in the balloon. We had a rate for that, dv dt, which was 2. I'm not going to include the units on that. Step 2, identify the variables and constants. So we have a few variables in this problem, right? We have volume. Volume was changing. It was based on time. We have our radius. Our radius was changing. It was also based on time. We have dv dt, our change in volume. We have our change in radius. Yeah, that was really sort of about it. We knew some of these things, right? We knew that dv dt was 2. We knew there was a relationship between volume and that, with volume and radius. We didn't know dr dt. Yeah. Anyway, number 3, writing an equation that relates all this. Usually, we're going to be dealing with volume formulas, maybe the Pythagorean theorem. There could be some other things, areas, maybe some other different formulas that we want to be working with. But it'll be a pretty common known formula for us. Step 3, take the derivative of both sides of that formula, whatever it was. So we took the derivative of our volume formula. Remembering to use the chain rule, right? It's very important when we take the derivative of a formula like this. We're usually going to be taking a derivative with respect to time. So each time we're taking the derivative of a variable that's not time, not t, we need to add on dv dt or dr dt, or maybe Pythagorean theorem, we have like a's and b's and c's. And then our final step, this is where we're actually going to be solving that answer that we really want to know. So you really want to know what quantity are you after, and what are all your known values, right? Do you know the radius or the volume or the change in volume or the change in radius or whatever other thing, right? You want to be really clear looking at your derivative function, whatever that derivative function ended up being, which we had something like this. right? Did we know everything but the one we want, right? You got to be able to know or figure out all the things but the one you want. We wanted dRdt, and fortunately, we knew these, so we could solve for it, right? If you have two unknowns, there might be some more work to be done. There might be some way to figure it out. Anyway, we'll go ahead and take a look at some more related rates here in future lessons. Thank you all, and bye.